On lecturing chapter 4 here. So remember, we went over chapter 3 to chapter 4. Chapter 3 has been up there on Canvas for a while now. Again, a recorded lecture. As we know, we just took the quiz, took up some time, and obviously on Monday we have a holiday as well. So we went into chapter 4, but again, you are responsible obviously for the stuff in that chapter 3 recorded lecture. So make sure you do watch it and all that good stuff, and this will hopefully keep us semi on pace here with the holiday coming up on Monday. Obviously, you don't show up on Monday, right? And all that good stuff. All right, so into chapter 4, we really started talking about the atom. We talked about some important experiments that sort of led to the understanding of the atom. And really the three sort of particles or subatomic particles that we find in the atom, and that's electrons, neutrons, and protons. Remember that early on, Thomson did a lot of work with CRT tubes along with a guy named Milligan. And really from that information, they were able to figure out the mass of an electron, which was 9.09 times 10 to the minus 28 grams. At that point, as we talked about, there was sort of an idea or a thought of the atom as being one that is referred to the plum pudding model of the atom, like we see here in this picture. And again, that was sort of the early idea of the model of the atom based on the fact that the existence of electrons obviously were sort of discovered there by Milligan and Thomson. The idea here was they would believe that atoms were neutral. So the early idea was this positive charge, all this red part in here, this positive charge spread out with the electrons embedded inside. And as we talked about, that was sort of the accepted model of the atom until really the next major event happened, which was Rutherford's gold foil experiment. And as we talked about last time, what they basically did is they shot alpha particles, which are these positively charged particles, at pieces of gold foil. And remember that when we get things that have the same charge, they sort of repel each other, and things that have opposite charges, right, are attracted to each other. So the thought was, as we talked about last time, that when they would shoot these positively charged radioactive particles that are moving pretty fast through this sort of mush of positive charge, they would expect it to be able to sort of bounce through, but they did expect it to sort of do some deflection and kind of deflect a little bit as it sort of punched through that big spear of positive charge. And as we talked about, I think at the end last time, what was sort of surprising when they did their experiment was that they found, for example, that most of them just sort of sailed right through, sort of no problem. But they did notice that every now and then these alpha particles would be scattered at large angles, which is what we see here, one scattering there, you know, these kind of larger angles sort of happening. And as we talked about, what that basically meant was they sort of had to sort of think about the structure of the atom and really sort of throw out the early model there, that plum pudding model, and sort of come up with a new version of the atom that sort of accounted for what they really saw happen in their experiments. And as we talked about, I think at the very, very end, they basically came up with the idea of the atom being mostly empty space. And again, that's what essentially accounts for those alpha particles pretty much sailing right through, no problem. It did contain, as we talked about, a dense positive core, which is what they referred to as the nucleus. And as we'll talk a little bit more about today, in the nucleus is really where we find protons, which are positively charged. And later on, obviously not at this point in time, but in 1931, neutrons were also discovered to be found in the nucleus as well. And that also is something that has no charge. Basically, the neutrons have no charge. So this really positive core, this nucleus, accounts for why they saw those alpha particles deflect out at a very large angle. It had to hit something very, very densely positive in order to make those alpha particles really scatter at those distances. The idea as well is that the electrons are moving around in that empty space. which is sometimes referred to as sort of the electron cloud. So that's sort of the area where it's moving. And again, it does move in a pretty random pattern there about the nucleus. And the other major difference between sort of the early model of the atom and really the modern model of the atom is that most of the mass is made up of the nucleus. And that does make sense, as we will see, I think, some numbers here in just a second, but a proton is 1,840-ish times heavier than an electron. A neutron is also around that amount, 1,800 or so times heavier than any electron. So within the nucleus, where we do have our protons and neutrons housing, each of these guys individually are about 1,800 times heavier than any electron that's basically flying around. And that is why most of the mass of the atom is made up of the nucleus, because it does contain basically those two particles. Any questions on that there? I think that's where we kind of left off last time, if I'm not mistaken. Okay. So as I mentioned, the atom does consist of our protons, neutrons, and electrons. Again, that dense core in the center has both our protons, which are positively charged, +1, by the way. Neutrons have no charge. And again, our electrons, which are negatively charged, are really flying around that empty space. As we also talked about, I think last time, there is an attraction between the positively charged nucleus and those negatively charged electrons that are flying around. Is that opposites attract. That's really why, again, not all the electrons just leave. They're sort of tethered to the nucleus in a sense. They can't really go too far. Also why some electrons actually can sort of leave, and those are the ones that are furthest away from the nucleus. They're not held as tightly as guys that are closer to the nucleus. So that's an important aspect of, as we'll talk about in some other chapters, why in certain cases only certain electrons are involved in things like bonding and stuff like that. And it's really for the reason, you know, if you think about just two atoms, badly drawn here, we got electrons and on the outside of each. Basically, when they come together, it's obviously the electrons that first come in contact with each other in that electron cloud. And that's really the basis of a bonding, is really just electrons being involved in all types of bonding. Ionic bonding, which we'll talk about in a later chapter, covalent bonding. It really involves either the transferring electrons being shared by things. Breaking and making bonds essentially require electrons being moved around. So really most chemical sort of reactions basically involve electrons. And in most cases, they really don't involve protons or neutrons. Those guys that are in the nucleus for normal chemical reactions are really not involved in anything that happens there. The only time those guys actually do get involved is when you deal with something that's like a nuclear reaction, and then it actually does involve the protons and the neutrons. We actually don't cover that chapter in this class anymore, but in those cases, you know, the elements will change and stuff like that because those guys are involved. But in normal regular chemical sort of reactions that occur, it is just really those electrons. One aspect of the atom is the mass of an atom, and one way that we sometimes refer to it is through what is known as an atomic mass unit, and that is AMU. It's sometimes abbreviated. AMU stands for atomic mass unit, and we could look at the mass of our protons, our neutrons, and our electrons here, and it is really based off of an isotope of carbon, which is the carbon-12 isotope. And the carbon-12 isotope basically has 6 protons, 6 neutrons, and a mass of exactly 12.0 AMU. Another place that you could kind of find the atomic mass of things are on the periodic table. If you look underneath the number that is underneath the symbol, that is the atomic mass of each of those elements. And we'll talk a little bit more about how we get to those numbers in just a second. But if we look at the proton has a mass of 1.007 AMU. And that is slightly less than our neutron, which has a mass of 1.008 AMU. And you can see here, our electron is the least massive of all of them at 0.00055 AMU. And that's roughly that number I gave you earlier, which was 9.09 times 10 to the minus 28 grams if you do the conversion. But what we see here is out of the 3 subatomic particles, the one that is the heaviest is actually the neutron, just barely. It just barely edges out the proton, which are very close to another. And again, like I said, the electron is approximately about 1,840 times less massive than the proton or neutron. So that electron really makes up less of the mass that we see here. Here again is our locations of everything. Proton and neutron, which was discovered in like 1930s by a guy named Chadwick, are found in the nucleus. Again, our electrons are outside the nucleus, traveling in that sort of empty space or electron cloud, again in a random motion as it moves around the nucleus. Any questions on that there? All right, so let's talk about these. Which of the following subatomic particles fits each description? Found outside the nucleus should be the electron. Has a positive charge should be proton, and has no charge would be neutron. Sounds good. Looks like a winner. All right, let's take a look at these. True or false? The mass of an electron is greater than the mass of a proton. That is false. Again, the one that is the heaviest is the neutron, just barely. The proton is right there, but the neutron barely takes the lead. Protons have positive charge and electrons have negative charge. That is both answers. So we'll go with true on that one. Protons are positive, electrons are negative, right? So that is true. And the nucleus of an atom contains only the protons and neutrons. That is also true. Again, that's where they are housed within the atom. Any question on any of those there? So here is sort of a visual representation again of the atom. And like we can see, you know, the nucleus is really small. The atom itself is relatively small. You can think of the atom as like a football stadium, and like the nucleus is like, you know, something like a marble on the 50-yard line. That's sort of, you know, what you can visualize it. This kind of bluish stuff that you see here, sometimes it's red. This is what is sometimes referred to as an electron cloud, an electron density map. And it might be hard to see up there. Probably it is. But if you could kind of see it, or you'll probably see some pictures in your book, you'll sometimes see this sort of cloud drawn like really kind of dark. And then it sort of gets lighter as it kind of goes out. And that's basically what is sometimes referred to as an electron probability map or density map. And usually in the darker areas of that cloud is a higher probability of finding an electron there. And as you kind of move out to the areas that are a little bit lighter in color, there's less of a probability of finding an electron there. Again, that just means that there's a good chance of finding an electron in those areas. It doesn't mean we have any idea how it's moving, how it got there, when it's going to be there, but it's just a pretty high probability. And that does make sense based on what we talked about, since that area near the nucleus is going to be a high probability of finding electrons because of that opposite attraction between the negatively charged electrons and the positive nucleus in that case. Any questions on the structure of the atom? You obviously need to know the structure of the atom. You need to know obviously where protons, electrons, and neutrons are located. You know which one is the most massive, obviously least massive, their charges. You should have some familiarity with some of those experiments that we talked about in terms of the other day, what happened there. And I think we also talked a little bit about Dalton's atomic theory, I think, as well at the very beginning. So those kind of things as well. Any question on any of that stuff? Okay, so we're going to continue talking about some other sort of aspects of an atom, and 3 important things: the atomic number, the mass number, and what isotopes are. So we're going to start with the ideas I talked about a second ago, that pretty much most of the chemistry all the time in a normal chemical sort of reaction it's really all about the electrons. It's really the thing that occurs for a chemical reaction. One of the sort of reasons, if you will, why a chemical reaction takes place is basically what is referred to as an electron transfer. So that's one of the big reasons why we see an actual reaction take place, because what's really happening is we have some electrons being transferred from one place to the next. And that is why in normal chemical reactions, electrons are really, really important. It is the basis really of all bonding, like I talked about earlier, and we will definitely get back into that a little bit later on as well. The first really major number or idea of an atom that you should know is the atomic number. The atomic number is sometimes abbreviated with a Z. The definition of the atomic number is the number of protons there are in an atom. So if you know the atomic number, you'll know the number of protons. The good news is if you look at the periodic table there, go with oxygen, I think that's still 8. And if you look at the number there on top of the symbol, that is the atomic number. So that number on the periodic table, and again, can't really see that periodic table all that great over there. But every periodic table, when you find the symbol and you go above the symbol, that is the atomic number. If you happen to look at a periodic table, or to see the one that's on the wall there, if you look at all the atomic numbers on the periodic table, none of the numbers repeat. So every single element has its own atomic number. And that's a really important thing, because if you know the atomic number, or you know the number of protons, which is the same thing, you will know what element you're talking about. Or if you know what element you're talking about, you just simply need to go to the periodic table, find the atomic number, and you will know how many protons that element has. So the atomic number is really important. It can be found on the periodic table. Now, if we happen to have an atom that is neutral, and we know the number of protons which are positively charged, that means that we should have an equal amount of electrons which are negatively charged to give us an overall charge of 0, or being neutral. So the other thing that the atomic number can tell you is, if you're dealing with something that is neutral, it will tell you the number of protons for sure, and it can also tell you the number of electrons that are there. Again, they should balance each other out. But it is really important that if you are ever asked this question of what is the definition of atomic number, it is just the protons. Only the protons is really the definition of it. Side to that is, again, if you're dealing with something neutral, it will also tell you the electrons, but that is not really the definition of atomic number other than protons. If we look on the periodic table there for nitrogen, nitrogen has a 7 above it. That means the atomic number for nitrogen is 7. If we have a neutral, I'll spit that out, a neutral nitrogen atom, it would have 7 protons, which are positively charged. It would then have to also have 7 electrons to balance that out, which gives us an overall charge of 0. Remember, the neutrons have no charge, so it can't affect the overall charge of the atom because they're neutral. How do we know if something has a charge? It would be written right here. So if there's nothing written right there, you can assume that it is neutral. It does not have a charge. Any questions on that there? So the atomic number, Z, number of protons you find in the atom, again, easily found on the periodic table. Every individual element has its own atomic number and own number of protons. So out of protons, electrons, and neutrons, which one is the most important in determining the element? It is the protons. If I change the protons, I am changing the element, which means I will never find an oxygen with an atomic number of 7, because I know nitrogen is actually the atomic number 7. So they'll never have that way. So if you change the protons, you change what the element is, and every element, like I said, has its own specific number. The other important number is the mass number. The mass number is sometimes abbreviated with an A. The definition of the mass number is the number of protons and neutrons that you find in an atom. That's really important because if you take the mass number, which is the number of protons plus the number of neutrons, and you take what we just talked about a second ago, which is the atomic number, which is the number of protons, and if you subtract the two, number of protons cancel, and you can determine the number of neutrons. So if you take the mass number and you subtract it from the atomic number, that will give you the number of neutrons there are in an atom. Pretty much every single element has protons, electrons, and neutrons. The one exception is our good friend hydrogen, which is why years ago you sometimes see hydrogen on both sides of the periodic table. Hydrogen has some unusual properties, and one unusual property is it only has one proton and it has one electron. It has no neutrons. So hydrogen is the only exception. Every other element will have protons, electrons, and neutrons. Hydrogen, proton, and electron, no neutrons in that particular case. Now, when you are asked to calculate the mass number, the atomic number, the number of protons, electrons, and neutrons, those all should be positive whole numbers. So they all should be positive whole numbers. If I go to the periodic table and I look and see the number on the bottom there, is that the mass number? The answer is no, it is not the mass number, because as we just said, the mass number, atomic number, and all those things need to be positive whole numbers. And if you look on the periodic table, underneath every element symbol there, all those numbers pretty much are all decimal numbers. They are not whole numbers. What sometimes confuses people is the mass number that you calculate and the number you see on the periodic table are very close to one another, because that is the atomic mass, as we just talked about a second ago, and we'll talk a little bit more about later in this chapter. But that's actually the atomic mass. So the mass number is not found on the periodic table. It is only the atomic number that you find on the periodic table. If you are asked to calculate protons, electrons, neutrons, mass number, atomic number, you'll be given enough information in the problem to do so. But definitely only the atomic number, the top number there, the number of protons, is found on the periodic table. So do not be the person that writes decimals for mass number. Happens on every exam. Don't do it. It's wrong. If you remember nothing else, remember that's wrong as you start writing the decimals. Yeah, stop at that point and try to figure it out another way. All right. In most cases, isotopes are really the same element, but they have different masses. So isotopes are the same element, but have different masses. And this is one of those things on Dalton's atomic theory, which was not correct. Now, in order for them to be the same element, is it the protons, electrons, or neutrons that has to be the same? Which one? It has to be the protons has to be the same, right? For them to be the same element. So isotopes are the same element, which means they have the same number of protons, but they differ in the number of neutrons. So it's the number of neutrons that makes it an isotope of each other. They have different number of neutrons. So for example, hydrogen has one proton, no neutrons. Deuterium, which doesn't sound like hydrogen, but is actually heavy hydrogen, is referred to sometimes, has one proton and one neutron. And tritium, which also doesn't sound like hydrogen, is the radioactive version of hydrogen, and that has one proton and two neutrons. A very common way that we write sort of the symbols for isotopes is what we see down here. We use the element symbol, and on the top left goes the mass number. On the bottom left goes the atomic number. So that's a very common way that we do it. So if we were to write the symbols for each of these isotopes here, we would do it by the following. You would look at hydrogen and it tells you it has one proton. Let's just say, for example, you're not sure what the symbol of hydrogen is. I imagine it might be. You could go to the periodic table and you find number 1. And number 1 there is H for hydrogen. The atomic number would be 1, which would go on the bottom left. The mass number, which again is the number of protons plus the number of neutrons. In this case, 1 plus 0 equals 1 for the mass number, and the 1 would go up on top left. Again, mass number up here, and atomic number here. If we take the top number and subtract the bottom number, 1 minus 1 is 0, and that will tell you how many neutrons it has, right? So if you see a symbol written like this, you can take the top number minus the bottom number, and it will tell you the number of neutrons in this case. If we go to deuterium, which again, if you read that name, you might not scream hydrogen in your head, but what should scream hydrogen in your head is when you see it also has 1 proton. You again could go to the periodic table, and number 1 is still hydrogen. So we would use hydrogen symbol. The atomic number would still be 1. In this case, the mass number would be, it has 1 proton and 1 neutron, which is 2. So the mass number for deuterium would be 2 and look like this. And lastly, if we did tritium, which again, if it didn't scream hydrogen to you, and they told you it had 1 proton, you could go to the periodic table. You again would see it really is hydrogen, even though it has a different name. Also the same atomic number, which would be 1, that should go on the bottom left. The mass number for tritium would be, it would be 3. It is 1 plus 2 there, gives you 3. And that would be the mass number that goes here. So these would be the symbol for hydrogen. Deuterium, and this would be for tritium. Any questions on that? And again, for the other two, you could do the same thing. For deuterium in the middle, 2 minus 1 is 1 neutron. For tritium, 3 minus 1 is 2 neutrons. Again, subtracting top number from the bottom. Any questions on that there? Now, this is a very common way that isotope symbols are written. Another very common way is something like this, Cu64, for example. Cu is copper. And what do you think the 64 represents? Is that the atomic number or the mass number? If we weren't sure what the atomic number was for copper, where could we find it? On the periodic table, yeah? So if you got a periodic table, look up copper, which is Cu. Above it should be a number with like a 2 and a 9, I hope, right? Got 29? That's good. I've seen it once or twice. That's good. So that 29, which we get from the periodic table, it's actually its atomic number, which means in this case, the 64 most likely is the mass number, yeah? So this is another common way that sometimes isotopes are written. We would, if we wanted to convert that into the symbol like we did before, we would write Cu for copper. The 29, which is the atomic number, would go on the bottom. And the 64 here would go on top, which is the mass number. And out of curiosity, how many neutrons would that guy have? How do I find neutrons? I take the mass number minus the atomic number. So in this case, it would be 64 minus 29, 35. Yeah. Everybody with me on that? Yeah, 35. So that'd be 35 neutrons. Yeah. Like out of the way, it would be 35 neutrons there. So That is, again, a very common way you could do it. And again, top number minus the bottom number there will give you the number of neutrons. We can see in every one of these cases, the protons, the neutrons, mass number, atomic number, all whole numbers, no decimals anywhere in any of these things. So just keep that in mind. Very common sort of error there. Any questions on that there? All right, why don't we try some here, see how we do. All right, so for each of these, want to determine how many protons, electrons, and neutrons there are. So take a couple minutes, see what you come up with, the number of protons, electrons, and neutrons in each of these. Okay, let's take a look. So again, when we see sort of the symbols written like this, remember that our top number here is our mass number, and our bottom number is our atomic number. And in this particular case, again, we would be looking in this region here for any type of charge, which obviously we do not see in this case. So we could safely assume that it is neutral. So here, this would have how many protons then? Yeah, it would have 27, which would match our atomic number. Because it is neutral, it should also have 27 electrons. Again, that all balances out to an overall charge of 0. And neutrons in this case would be, yeah, so number of neutrons would be our mass number, which is 60 minus 27, and looks like 33 there. Any questions on that one there? That's cobalt, by the way, coming down to Cl, which is chlorine. Again, we'll look over here. We don't see anything written, so we know it's neutral. We see that our atomic number is 17. So that should tell us in this case, number of protons is 17. Again, because it is neutral here, it should have an equal number of electrons, which would be 17. And again, adding those together gives us an overall charge of 0. That leaves us our neutrons, which again, we should take our mass number, which is 37 in this case, minus our atomic number, which is 17. Looks like a 20, it looks like in that case. Any questions on that one there? Lastly, here we got U, which is uranium. Same deal, nothing written there. So we could safely assume, again, this one is neutral. Looking at our atomic number, the number of protons should be 92, with a matching number of electrons in this case, since it is neutral, again, adding up to 0. Number of neutrons in this case is a lot, 238 minus 92, like a 146-ish, yeah, give or take. Give or take a neutron here or there, I suppose. Any questions on how to calculate any of those there? Okay. Then let's take a look at some here where we'll write the symbol. So why don't we start with this first one here? We will have krypton that has 48 neutrons. So write the symbol with the mass number and the atomic number. Periodic table probably would be helpful. I would say you could look at the one on the wall, but maybe you can see it. I don't know. But if not, you might want to look at one that you got with you. Okay, let's take a look first at this one here. So symbol for krypton is K. KR sounds good. We also, from the periodic table, can find an important number, and that number is the atomic number, which should be the number above it. Still 36, I hope, yes. That should go bottom left. 36 also tells us that's the atomic number, but that also tells us that we have 36 protons in that case. And that's important along with our neutrons, because if we add those together, that will give us our mass number that we need. And that would be obviously 36 plus 48, 84, which would be our mass number, right? And that should go upper left there as 84. Any questions on that one there? Okay. All right, let's try this one then. Let's do nitrogen that has 6 neutrons. So write the symbol, see what you come up with. All right, so on this one, if we look up on the periodic table there for nitrogen, we should see hopefully an N and a 7 there. That tells us that the symbol should be N. Again, from the periodic table there, we could pull the number from above, which is our atomic number. That would go on the bottom. Also tells us that this guy has 7 protons. Adding these guys together, the protons and neutrons, which is your definition of mass number, gives us a lucky 13 there for the top. Yeah. Any questions on that one there? And lastly here, we want to write the symbol for iron that has a mass number of 56. We also want to figure out how many protons, electrons, and neutrons it has. So take a second there, see what you come up with. The symbol for iron is, it is Fe. Again, from the periodic table, we could get the atomic number, which is 26. Yeah, it should be 26. That would be the atomic number, which would go on the bottom. The mass number, which they gave us, would go on top, and that would give us 56 up on top, 26 on the bottom. That would also tell us, in this case, the number of protons iron has is, the number of protons is 26. Number of electrons would be 26. Number of neutrons would be 30. 56 minus 26, which is our mass number. So it would have 30 neutrons in that particular case. Any questions on how to figure out protons, electrons, neutrons, mass numbers, any of those questions? What happens though if something did have a charge, for example? So let's see. Yeah. Okay, let's say we had something actually with a charge. Let's say if we have something that has a charge, those things are what are known as ions. So ions are things that have charges. And there's really 2 types of ions. There are positively charged ions, which are known as cations. And those are positively charged ions. And there's also anions, which are negatively charged ions. So let's just say, for example, we took our nitrogen that we did previously here. And let's say that we had nitrogen 13, 7, and a -3 charge in this case. Now, in this case, it obviously has a charge. We can see it written there. And it is -3. So let's just start with the stuff we did before. The number of protons in this case is how many? Yeah, it's got to still be the same, right? Because if that changed, it would no longer be nitrogens. And obviously the atomic number is still 7. So number of protons here is 17. I'll spit that out. In this case, the number of electrons would be, number of protons should be 7. It's kind of like 17, but you know, with an extra 1 there. Let's try that again. Should be 7. That's better. The number of electrons should be, number of electrons would be in this case 10 electrons. That's 7 protons, which are 7 positive guys, and 10 negative guys leaves you a -3 left over. That is where the charge comes from. It has basically 3 more electrons than the neutral guy. That means it has 3 more negative charges than positive charges, leaves you a negative charge overall. By the way, the number of neutrons in this case would still be 6. 13 minus 7 would be 6. So this is an anion, and the way that we make an anion is it gains electrons. So does the charge help us understand what is going on? It actually does. The negative tells you it gained electrons. The number tells you how many electrons it gained from the neutral guy. So if you remember, the neutral guy over here had how many electrons? 7. This guy has a -3 charge. 7 and 3 is 10. It has 10 electrons. So it gained 10 electrons, or 3 electrons in that case, for a grand total of 10. Any questions on that there? Now, what happens? We took iron like we had there on the bottom, and we do 56 and 26, and it has a +2 charge. The number of protons in this case for iron would be, it would still be 26. I'm going to write the right number this time. That's good. In this case, it has a +2 charge, which means the number of electrons would be, it would be 24. 26 positives and 24 negatives leaves you a +2 left over. Again, that is where the charge comes from. In terms of neutrons, again, 56 minus 20 would still be 30. So when something gets a positive charge, what happens is, if we look at the neutral iron, it had 26 electrons. Our iron with a +2 charge had 24 electrons. So when you see a positive charge, it means that guy has lost electrons. And the number is how many it lost from the neutral guy. Went from 26 to 24. And that's how we get cations, by losing electrons. So when things lose electrons, they have more protons, which is why they become positively charged. When things gain electrons, they have more electrons than protons, which is why they become negatively charged. That is the basis of pretty much ions and ionic bonding, is things that gain charges. Again, the only thing that changes is the electrons. We could never change the protons. Again, for as we talked about, you would then be changing the element, which you wouldn't want to do. So it's only the protons that change. Question on how to do it with things with charges. Now, the chemical properties of elements are determined by protons and electrons in the atom. Neutrons really don't take place in normal chemical reactions. One of the nice sort of things about isotopes is, a lot of times isotopes, there are radioactive versions of elements that are isotopes. And, you know, if you had, for example, we just had copper-64, which is a actually radioactive version of copper, and you had regular copper. They both basically are copper. They behave the same way. So one practical aspect of using, for example, a radioactive version of an isotope is, if you're interested in what happens with copper, say in the body, or some type of mechanism, you can use a radioactive version of copper. It will do the same chemistry as regular copper, but you'll be able to follow where the copper goes by following the radioactivity. So it's a really common practice that people do in research labs, is they use a lot of times radioactive version of elements, and they can use it like a tracer. Basically, they'll really follow what's happening with that particular element or whatever it may be, because again, it will basically do the same chemistry as the non-radioactive version of it. Any questions on that there? All right, talk a little bit about chemical composition. One of the fundamental properties of an atom is its mass. It is obviously related to the number of protons, electrons, and neutrons that there are in the atom. Obviously, an atom is extremely small. You can't really pick it up and like put it on a scale or anything like that. So typically speaking, whenever we run into a situation in chemistry where we can't necessarily maybe directly measure something, a lot of times what we do is sort of pick something to use as a standard to compare everybody to. And for atomic mass, they basically picked the standard carbon-12 isotope. Let's get too many pictures. No, I didn't. We'll go there. They used the carbon-12 isotope as the sort of isotope to figure out the atomic masses of everybody that's there. The carbon-12 isotope has a mass of exactly 12 AMU, as we saw just a second ago. And they basically go, okay, you know, hydrogen is only about 8.4% as massive as a carbon-12 isotope. And they could do a very simple calculation That is 8.4% converted into a decimal, right? Divide by 100, move the decimal place 2 places to the right, times it by 12, gives you roughly a number of 1.008 AMU. If you look on the periodic table underneath hydrogen, that is the number that you will see there, 1.008. You could also see similar calculations for everybody on the periodic table. And pretty much, as we just talked about, it is not the mass number that we see on the bottom there, but that is the atomic number. Atomic mass. Spit that out, right? So that is the atomic mass that we do find on the bottom of the symbol on the periodic table. Now you may look at carbon, for example, on the periodic table. And the number that you'll actually see for carbon is 12.01. You may say to yourself, well, if they use carbon as the standard and it has a mass of 12, why, when I look at carbon on the periodic table there, is it 12.01? And the answer is the values that we actually see on the periodic table are actually average atomic masses. And they are the average atomic mass of all the naturally occurring isotopes for that particular element. So for example, carbon, there's the carbon-12 isotope, and there's like the carbon-13 isotope. And an average value of those two guys gives you an average value of 12.01. Although most people do not call it an average atomic mass, they just call it atomic mass, but they really are calculated by taking the sort of average value of each of the naturally occurring isotopes. So how do you do that calculation? There's sort of a formula that you follow if you want to calculate the atomic mass of an element in AMU. You basically take the percent abundance of the first isotope and you times it by the atomic mass of the first isotope. Then the important part is you add it, not multiply, but you actually add it to the percent abundance of the second isotope times the atomic mass of the second isotope. And if you had 3 isotopes, you would follow that pattern. If you had 4 isotopes, you keep following that pattern for however many isotopes that you have going on there. What is the percent abundance? The percent abundance, sometimes called relative abundance, is basically the percentage out of 100 of that isotope, how much it occurs. So for example, maybe the carbon-12 isotope occurs about 98% of the time, and the carbon-13 is like 1% of the time. That's basically what the percent abundance is. So I think we have the numbers on the next slide. We'll kind of see how we could calculate that here in just a second. And again, if you have 3 naturally occurring isotopes, again, you just continue this pattern of the percentage times the atomic mass. Obviously, when you use a percentage in a calculation, you should convert it into a decimal. Yeah. So you got to divide the percentage by 100 or move the decimal place 2 places to the left there. But you don't want to leave it as a percentage, you know, when you do this calculation. So here is this calculation here. So for carbon, this is the carbon-12 isotope. We know that because that's the mass number. That is the carbon-13 isotope. The atomic mass for carbon-12 is 12.00 AMU. For the carbon-13 is 13.003. As I said before, the carbon-12 isotope occurs almost 99% of the time, 98.97%, and 1.11% for carbon-13. So if we were to do this, like we have down there, the atomic mass would equal our first isotope, which is the carbon-12. You can move the decimal place 2 places to the left. It'll be 0.9897, which is 98.97% divided by 100, basically. You could do that too if you want to divide it by 100. We would times it by 12.000 AMU. And that is our first isotope. We then would add it to the percentage of our second isotope, which is 1.11%. Again, you could either move the decimal or do this move, divide it by 100. will move the decimal for you if you want to do that. And then we can times it by the atomic mass of that isotope, which is 13.003 AMU. When we do all that good stuff, we should end up with 12.01 when you put it into your calculator. And that is the number that we see on the periodic table when we do look underneath carbon. And again, that is how you calculate basically the atomic masses you see on the periodic table underneath the elements by taking all the naturally occurring isotopes and doing this calculation. By the way, if you're not sure you have all the naturally occurring isotopes for an element, the percentages all should add up to 100%, right? So obviously, if they don't add up to 100%, you're missing a percentage. If you have two percentages for two isotopes and one you don't have, you could add those together and subtract from 100, right? And that'll tell you the percentage for the missing isotope. Any questions on that there? Okay, we will lay it up there.